I want you to picture something for a second, and I guarantee you know exactly what I'm talking about. Somewhere in your home, there is this very specific drawer.
Oh, yeah. I think we all have one.
Right. It's the drawer of dead cables. You pull it open, and it is just this tangled, chaotic nest of obsolete plastic and wires. You've got mysterious dongles, random power bricks, charging wires from 3 phones ago,
Mm.
maybe some bizarre adapter you used exactly one time in, what, 2014?
Yeah, that sounds painfully accurate. It genuinely looks like an archaeological dig site of just technological frustration
Exactly.
because every layer in that drawer represents a different era,
Mhm.
an era where hardware engineers basically hit a wall and had to invent a new physical shape just to push more power or more data through a connection.
Well, today we are finally bringing order to that drawer. We are doing a deep dive into some study notes from Professor Messer's CompTIA Plus 220 1201 certification course.
Which is a fantastic resource, by the way.
It really is. But before you start thinking we're just, reading from some dry IT textbook to help someone pass an exam, let me assure you, we are using this curriculum as like a master blueprint. We are going to decode the underlying architecture of how your mobile devices actually talk to the world around them.
Right, because it's not just random cables. It's an entire ecosystem.
Exactly. Our mission is to take these technical specifications and really show you the brilliant and sometimes honestly chaotic logic of how our personal tech ecosystem functions. By the end of this deep dive, you won't just know what's in that drawer. You'll understand how to relentlessly optimize the hardware you rely on every single day.
And that's so important. I mean, understanding the mechanisms, the actual why and how behind the hardware, it changes your entire perspective.
It totally is.
You stop seeing just a random collection of cords, and you start seeing this highly evolved system of data and power delivery.
So let's start at the very bottom of the drawer with the physical wired connections.
Hmm.
If you look at older legacy hardware, I mean, the sheer variety of USB connectors is staggering.
Oh, it was a mess.
You have the mini B, the micro B, and then that classic chunky Type A connector that we still, for some reason, plug into desktop PCs. And interacting with those always felt like a physical puzzle.
It really did.
Like you plug it in, it doesn't fit, you flip it over, it still doesn't fit, you flip it a third time, and somehow, miraculously, it goes in.
Right, the classic USB paradox. But you have to remember, the physical constraints of those legacy designs were strictly unidirectional. The internal plastic block and the little metal pins, they were engineered to only make contact in one highly specific orientation.
Which just seems so short-sighted now.
Well, yeah. And as the industry pushed for thinner, lighter mobile devices, embedding a relatively massive unidirectional port like a Type A or even a Micro B, it became a serious bottleneck for hardware designers. I mean, they simply ran out of physical real estate inside the phone's chassis.
I hear that, but I have to push back on a historical point here. USB literally stands for Universal Serial Bus. The entire goal was a universal standard. So why did Apple fracture the market by creating their own proprietary Lightning cable? Because a lot of people view that as a super cynical move that just, added a completely different family of white cables to that drawer.
And it is incredibly easy to view it that way through a modern lens.
Hmm.
But you really have to consider the engineering reality of the time. When Apple introduced Lightning, they weren't just trying to be difficult.
Really? Because it felt like it.
I know. But they were actually solving the exact structural flaws of legacy USB that we were just talking about. The Lightning connector utilizes an 8-pin architecture. And crucially, it was engineered to be completely reversible.
Okay, that was a game changer.
Exactly.
Yeah.
The device's internal port dynamically routes the power and data depending on which way the pins make contact.
Yeah.
And furthermore, it allowed for significantly higher power output than the standard USB configurations that were available at that specific moment.
Which meant faster charging.
Much faster charging times for iPads and iPhones. Apple essentially bypassed the somewhat sluggish consortium of universal standards to deliver a mechanically superior solution for their own ecosystem.
So they sacrificed universality to solve the immediate user friction, like they fixed the flip it 3 times problem.
Precisely. But the broader industry definitely recognized the necessity of that solution. And that pressure eventually led to the development of the modern standard that surpasses pretty much everything before it, which is USB-C.
Yes, the cable that is finally standardizing the drawer.
Right. And the sheer engineering packed into a USB-C connector is just phenomenal. We are no longer talking about 4 8 pins. USB-C houses 24 separate pins inside that tiny reversible housing.
Wait, 24 pins in that tiny plug.
Yeah, 24. And this isn't just about moving serial data slightly faster. Those 24 pins allow for a concept called alternate modes.
Okay, what does that mean for me?
It means the cable can support entirely different signal types simultaneously on the exact same physical wire.
Oh, wow. How does that actually work in practice, though? How does one tiny wire manage all that traffic without getting scrambled?
So think of those 24 pins as a multi-lane superhighway, right? But the lanes can be dynamically reassigned on the fly.
Okay, I'm tracking.
A portion of the pins can be dedicated entirely to delivering massive amounts of electrical power, easily enough to run a high-end laptop. And at the exact same microsecond, other pins are operating as dedicated lanes for DisplayPort or HDMI video signals.
Pushing like 4K video to a monitor?
Exactly, pushing 4K resolution to an external monitor.
Mm.
And simultaneously, the remaining pins are operating under the Thunderbolt protocol to transfer massive data files. It entirely replaces those older USB 2.0 limitations because the architecture is multiplexing power, heavy data, and ultra-high-definition video simultaneously.
That's wild. So the dream is actually real. We consolidate the heavy power brick, the thick braided video cables, and the data lines into one 24-pin standard.
That's the reality now, yeah.
But even with that incredible bandwidth, a physical cable still anchors you, right? Like you're stuck to a desk or a wall outlet. The ultimate endgame of mobile computing isn't just a better wire, it's eliminating the wire entirely. Which takes us right into the invisible web of wireless connectivity protocols.
Exactly. This is where we shift from physical pins making electrical contact to basically manipulating radio frequencies to transmit that exact same data through the air.
The A-plus notes highlight two primary players here for device-to-device communication. We've got NFC, which is near-field communication, and Bluetooth. Now, Bluetooth creates what the curriculum calls a PAN, a personal area network.
Right, a PAN.
And that's meant for high-speed, short-distance connections like your wireless headsets, your external keyboards, your mice.
Yeah, a personal area network is essentially this continuous, invisible bubble of high-frequency connectivity that travels with you. Your phone or your laptop acts as the hub, broadcasting outward to maintain an active link with all those peripherals simultaneously, usually over distances up to about 10 meters.
Okay, so if Bluetooth creates this robust, high-speed bubble that can handle all my peripherals across a room, why do hardware engineers waste space and battery life, including NFC chips?
That's a really common question.
Right, because NFC only transfers tiny amounts of data over incredibly short distances, like tapping your phone at a grocery store checkout or sharing a contact card by literally bumping phones together. What is the functional point of NFC when Bluetooth is so powerful?
It really comes down to the physics of intent and security. Because a Bluetooth PAN is a broad radio broadcast, your device is constantly shouting its presence to any compatible receiver within 30 feet.
Oh, I see where this is going.
Yeah, you absolutely do not want your phone broadcasting your credit card data to every single point-of-sale terminal you happen to walk past in a busy mall.
That would be an absolute financial nightmare.
A disaster. So NFC solves this through magnetic induction. The transmission field is physically limited to just a few centimeters. The engineering requires you to physically tap your phone to the terminal.
Ah, so it's intentional.
Exactly. That required physical proximity inherently proves human intent. You have to intentionally move your device into that microfield to execute the transaction.
Like a digital secret handshake.
That's a great way to put it. And this is also why the A+ notes specify NFC for access control. Corporate buildings use wall sensors, where you tap a smartphone or a smartwatch to unlock a door instead of swiping an ID card.
Because you want the door to unlock only when the user deliberately taps the panel.
Right, not merely when they walk down the hallway near the door and their Bluetooth happens to connect.
That makes total sense. The limitation is actually the feature. The short range is the security mechanism.
Precisely.
Now, speaking of these wireless networks, the sources also dig into how we share actual internet access from our mobile devices. And I notice people use the terms hotspot and tethering interchangeably all the time.
Not constantly.
But structurally, on a network level, they are operating very differently, right?
They're completely distinct network architectures, even though the end result for the user feels pretty similar. And it's worth noting that both functions are entirely dependent on the software permissions granted by your cellular provider.
So let's break down the mechanics. A hotspot turns your smartphone into a full-fledged Wi-Fi router. It takes your cellular data connection and broadcasts a Wi-Fi signal to many devices. So your laptop, your friend's tablet, maybe another phone.
Right.
But tethering, on the other hand, is a strictly one-to-one relationship. You are sharing your internet connection with just a single device, usually routed over a dedicated Bluetooth link, or even directly through a physical USB cable.
Yeah. And to really understand the difference, you have to look at the processing overhead on your mobile device. When you activate a hotspot, your phone is doing some heavy lifting.
Because it's acting as the router for everyone.
Exactly. It's assigning IP addresses, managing network traffic for multiple clients, and handling the network address translation for all those connected devices. It drains the battery aggressively.
I've definitely noticed my phone gets super hot when the hotspot is on.
Yeah, that's the processor working overtime. But tethering over a USB cable creates a single direct pipeline to one operating system. The phone acts more like a simple modem, just passing the connection straight through.
Okay, so we have the physical infrastructure of USB-C, and we have the invisible routing of our PANs, NFCs, and hotspots. But all of this data processing is honestly kind of useless if we can't interact with it on a human level.
Right, you need an interface.
Phones and tablets have built-in screens and microphones, but they are incredibly constrained by their physical size. Which brings us to how we upgrade the sensory experience with specialized accessories.
Because base hardware is always a compromise of space and cost. To get, professional-grade utility out of a mobile device, you have to bypass those integrated components and interface with external hardware tailored to your specific sensory needs.
Let's look at audio headsets. You obviously have wireless Bluetooth options, but the curriculum details several wired avenues too: USB, Lightning, and the classic analog audio jack. And the technical breakdown of that analog jack is really fascinating.
It's an absolute classic piece of tech.
The A+ notes refer to it as a TRRS connector. Now, I have been jamming headphones into devices my whole life without knowing that stands for tip, ring, sleeve.
A lot of people don't. But it is a brilliantly simple, purely mechanical design. If you inspect a standard 3.5mm headphone plug, you'll see it's divided into isolated metal segments separated by these little plastic bands.
Right, I always wondered what those little black rings were for.
Yeah, so the tip is the very end, the sleeve is the base near the cable, and those basically sandwich two distinct ring connectors right in the middle. When you push that plug into the jack, physical metal contacts inside the port literally snap into place against those specific segments.
So the physical separation on the plug maps to different audio channels?
Exactly. Each distinct segment acts as an isolated electrical pathway. One carries the left audio channel, another carries the right audio channel, one carries the microphone input, and the final one serves as the electrical ground. It's an entirely analog transmission of the sound wave.
I just love the elegance of that analog engineering. But I have to ask, in a world where we just talked about 24-pin multiplexed USB-C and ubiquitous Bluetooth networks, isn't that analog TRRS jack a total dinosaur?
You'd think so, wouldn't you?
Yeah, like why maintain dedicated analog wiring when we have all these sophisticated digital protocols?
Because digital protocols require processing power, and processing power requires batteries. Imagine you are an emergency dispatcher, or you're a remote worker on a critical client presentation, or simply on back-to-back calls for 8 hours straight.
Okay, yeah, that's a lot of talk time.
Right. Bluetooth headsets drain battery, and they introduce these tiny amounts of latency as the audio is encoded and decoded over the radio frequency. If your battery dies mid-sentence, that sophisticated digital convenience immediately becomes a massive operational liability.
Oh, it's the worst. You are scrambling to switch inputs. The client is saying, "Hello, are you there?" And you're just frantically trying to talk into the tiny little hole on the bottom of your phone.
We've all been there. It's incredibly stressful.
Hmm.
But a dedicated wired TRRS or USB headset provides absolute reliability. A physical copper wire does not suffer from radio interference, it has zero noticeable latency, and it draws its minimal power directly from the device. For consistent, mission-critical communication, the wire remains supreme.
Okay, that makes perfect sense. And that modularity extends to visual and tactile inputs as well. The sources mention upgrading your phone's audio output with battery-powered Bluetooth speakers or, bypassing a laptop's terrible built-in camera with an external USB webcam for high-fidelity video conferencing.
Absolutely. The built-in webcams are usually an afterthought.
They really are. But the tactile accessory that stands out the most here is the active stylus. And we're not talking about those cheap, squishy plastic sticks from the 90s. These are wireless Bluetooth pens with incredible pressure sensitivity and programmable physical buttons.
Yeah, they turn a simple blast capacitive touchscreen into a highly precise digitizer. The hardware inside the stylus communicates the exact angle, the tilt, and the pressure back to the tablet's processor in real time. It mimics the physical friction and flow of a real pen on paper.
But the curriculum notes a pretty severe caveat here regarding ecosystem compatibility.
Yes, and this is crucial, because the communication between an active stylus and the screen requires such intense, low-latency data exchange, you really cannot rely on a universal standard. The notes use the Apple Pencil as the prime example.
Right, you can't just use it on anything.
Exactly. It is hardware locked to specific Apple tablets and laptops. The digitizer in the screen and the Bluetooth array in the pen are engineered to handshake exclusively with each other. You cannot simply buy a high-end stylus off the shelf and expect granular pressure sensitivity on some random device.
You literally have to map the peripheral directly to the host architecture before you even buy it.
Yes, compatibility is everything there.
Okay, so at this point, we have optimized our mobile setup. We have the flawless 24-pin cable, the secure NFC protocols, the reliable TRRS headset, and a highly calibrated stylus. We are perfectly equipped to work from a coffee shop or an airport. But what happens when we take all this portable power and try to integrate it into a permanent stationary desk?
This is a really fun transition, actually.
Because this bridges us to the hardware that transforms a mobile device into a desktop replacement.
Exactly. This is where we see the most aggressive blurring of the line between a mobile OS and a traditional desktop workstation. The goal is to walk into an office with a 2-pound laptop and instantly interface with multiple monitors, hard drives, and wired networks without spending 10 minutes plugging in cables.
The A+ notes highlight two primary pieces of hardware to achieve this: docking stations and port replicators. Let's dissect the mechanical differences here because they matter. A docking station is highly specific hardware designed for a particular laptop model, right?
Yes, very specific.
The laptop usually physically snaps into the dock, engaging a proprietary high-bandwidth connection on the bottom or side of the machine. And the notes mention these docks can even support full-size interface adapter cards.
And that is the defining characteristic of a true docking station. Because it uses a proprietary physical connection, it is often tapping directly into the laptop's motherboard bus, like the internal PCIe lanes.
Whoa, wow.
Yeah, that allows the dock to house internal hardware, like a dedicated desktop graphics card or an internal network interface card. It radically expands the laptop's raw processing capability.
That is massive. So compare that to a port replicator. Replicators are those portable hubs you see everyone using at coffee shops now.
Exactly, the little dongles.
Right. They connect via a standard universal USB connection, usually our hero, USB-C. But because they use a universal bus, they don't support those heavy-duty internal adapter cards. Instead, they just replicate the basic ports. They provide a cluster of extra USB slots, HDMI outputs, maybe an SD card reader.
Right, they aren't adding processing power.
So, to frame the architecture, a docking station is like pulling a race car into a highly specialized pit stop where the mechanics actually bolt new engine parts onto the chassis.
We like that.
But a port replicator is more like a universal Swiss Army knife you plug into the dashboard. It gives you a lot of handy tools, but it doesn't change the underlying horsepower of the car.
That analogy holds up perfectly.
Yeah.
And in the modern hybrid workforce, utilizing either of these tools is just a game changer for productivity.
Oh, absolutely.
You leave your heavy peripherals, your dual monitors, your mechanical keyboard, your wired Ethernet connection permanently plugged into the dock or replicator on your desk. You arrive, make one single connection with your mobile device, and it instantly absorbs the physical footprint of a heavy desktop workstation.
And interacting at that hybrid setup introduces a couple of other specialized input devices. The curriculum covers the trackpad, which obviously replaces the physical mouse on a laptop. But we are well beyond just moving a cursor now. Trackpads utilize capacitive touch to interpret complex, multi-finger gestures.
Which is amazing software engineering.
It is. The hardware communicates with the OS so you can swipe with 3 fingers to switch applications or physically pinch the surface to manipulate elements on the screen.
Which is incredibly efficient, right up until the sensitivity that capacitive surface works against you. The A+ curriculum points out a very practical hardware control issue here.
Let me guess, palm rejection.
Exactly. If you are typing a long document on a small laptop chassis, your palm will inevitably rest on or brush against the trackpad. The OS can try to use software to ignore palm touches, but it frequently fails, causing your cursor to wildly jump to another paragraph while you're typing.
It is genuinely one of the most frustrating things that can happen while working. You look up and you've typed a sentence in the middle of a completely different paragraph.
It's maddening. So to solve this, manufacturers build in a hardware-level interrupt. The notes highlight how you can completely disable the trackpad surface at the hardware level, often using a specific function key combination.
Like pressing F and F10.
Yeah, exactly, which might have a small blue icon printed on it. This cuts the data transmission from the trackpad entirely, allowing for heavy, uninterrupted typing. And if you rely heavily on gesture controls but prefer to work on large external monitors, you can just introduce an external Bluetooth trackpad to your desktop setup.
The final accessory they cover really bridges the mobile and desktop environments perfectly. Drawing pads. If you rely on that precise, pressure-sensitive Bluetooth stylus we discussed earlier, but you want to apply that artistic precision to robust desktop software, you can connect an external digitizer pad via USB or Bluetooth.
Right. It takes the mobile-first concept of a touchscreen and transplants it directly into the stationary workstation environment.
Which is just so
It
cool.
is the ultimate synthesis of the two worlds. You maintain the massive processing power of the desktop environment, but utilize the granular tactile input methods perfected by mobile hardware.
Well, we have journeyed through an immense amount of architecture today. We started at the physical layer, tracing the evolution from those frustrating unidirectional USB plugs to the brilliant 24-pin multiplexing of USB-C. We explored how the invisible web operates, contrasting the localized, secure magnetic induction of NFC against the broad, high-speed broadcast of a Bluetooth personal area network.
We also unpack the heavy routing differences between broadcasting a hotspot to many clients versus establishing a direct tether to a single machine.
We broke down how a TRRS analog jack physically isolates audio channels to save our communication when digital batteries inevitably fail. And finally, we explored how proprietary docking stations and universal port replicators blur the hardware lines, allowing a thin mobile device to consume the capabilities of a full desk setup.
And, the essential takeaway from Professor Messer's curriculum isn't just memorizing pin counts or acronyms for a test.
Definitely not.
It is recognizing that every single piece of hardware in your ecosystem is a deliberate engineering choice. When you understand the logic behind a port replicator's bus limitations or why NFC is deployed for secure access control, you cease to be a passive consumer.
You become the architect of your own workflow.
Precisely. You become capable of optimizing your technology to serve your specific needs.
You take control of the ecosystem. And that leaves me with a final thought for you to consider. We've established that our mobile devices are now functioning as our secure physical keys via NFC, our digital wallets, our communication hubs, and, when attached to a high-bandwidth docking station, our primary desktop processing engines.
They really do it all.
They do.
Yeah.
So if a single pane of glass and a unified 24-pin cable can adapt to fulfill all of those roles flawlessly, how long will it realistically be until the traditional, standalone, immovable desktop PC tower is viewed as a total relic of the past by the average person?
It's a great question. It points to a future where the computing power is entirely ambient and portable, and the environment simply adapts to whatever device you bring it to it.
Something to ponder the next time you find yourself staring down into that drawer of dead cables, looking at the history of how we got here, and wondering what the future is going to look like. Thanks for joining us on this deep dive.